Hi, everyone. Welcome back to today's math channel. I'm your host, David Tear, and today I'm going to talk about perfect numbers and Mersenne primes. So let's begin. I'll start with perfect numbers. You guys may already be familiar with them. What is a perfect number? Well, a perfect number is just a number, a positive integer, such that the sum of all of its proper factors or divisors is equal to the number. So, for instance, 6 has proper factors 1, 2, and 3. We don't count 6 itself. And if we add those factors up, we get 1 plus 2 plus 3 equals 6. So it doesn't seem all that special, but it turns out these perfect numbers are very, very rare. And there's a few small ones. I mean, 28 turns out to be the next. 1 plus 2 plus 4 plus 7 plus 14. You can check that equals 28. 496, you can do the same thing. The factors are listed in the middle column. And if you add up all the factors except for 496, you'll get 496. Same for 8,128. So they're growing pretty fast, and these were, perfect numbers were of interest to the ancients, particularly. I think the ancient Greeks were interested in them, and you might wonder if there's a pattern to them. And it turns out there is. And the guy who discovered this pattern was a very famous Greek mathematician named Euclid, the same Euclid who came up with Euclidean geometry. What he discovered, I don't think he discovered all of these perfect numbers. These are all perfect numbers, it turns out, and they're all factored. I think he only knew the first four that were listed on the previous slide. But what he discovered was that if you factored them, you had this pattern. It was equal to a power of 2 times a prime. So, for instance, 6. 6 is 2 times 3. 2 you can write as 2 to the first power, and 3 is prime. As a matter of fact, it's not just any ordinary prime. It's what's called a Mersenne prime. I'll get to those in a few minutes. But Mersenne prime is just a prime that's equal to a power of 2 minus 1. So you can write 6, which is perfect, as 2 to the 1 times 2 squared minus 1. And similarly, 28, the second perfect number, you can write as 2 squared times 2 cubed minus 1. 2 cubed minus 1 is 7. That's also prime. And then you can keep going. The next one's 496. That's equal to 2 to the 4th times 2 to the 5th minus 1. 8,128 is 2 to the 6th times 2 to the 7th minus 1. And what Euclid proved was that every even perfect number had this form. It was always equal to a power of 2 times the corresponding Mersenne prime, which is the next power of 2 minus 1, as long as that was prime. That's what he proved. He proved it in one direction, and this table just lists the first 8. So I don't think he knew about the last 4 on this table. They're pretty big, but those and then there's a theorem. Euclid proved one direction of it, like I said, and Euler. He was a much later mathematician. He was in the 18th century, very famous Swiss mathematician named Leonhard Euler. He proved in the other direction. So the theorem says that if for every number n that's even and perfect, every even and perfect number n has the form n equals 2 to the p minus 1 times m sub p. This is a typo, it should be m sub p. M sub p is 2 to the p power minus 1. You subtract 1 from the p power of 2. And if you multiply those together, you get even perfect number, and vice versa. If you have an even perfect number, always factors like this. That's what the Euclid-Euler theorem says, and here's the first 5 written out. I'll even write the sums of the factors out. But it's not known about odd perfect numbers. You might be wondering, what about odd perfect numbers? It doesn't say anything about it. Well, we don't know, but it's strongly suspected that there are no odd perfect numbers. I think most mathematicians nowadays think there aren't any odd perfect numbers. I don't think there are any, and the reason I don't think there are any is because if it's already known that if there are any odd perfect numbers, that they have to First of all, they have to have at least 1,500 digits, so they have to be really, really big. That's been proven. There's no odd perfect numbers with less than 1,500 digits. And also, we know that they have to be equal to a square times a prime, and already that's pretty restricting. And the third requirement is they have to have at least nine distinct prime factors. So they're, they have a lot of constraints on them, and so far nobody's found any, and it's strongly suspected they don't exist. But we do know about even perfect numbers, and we do know about their relationship to Mersenne primes. So I mean, it's enough to know about Mersenne primes. If you want to find as many even perfect numbers as you want, you just look for the corresponding Mersenne primes. And so I think the shift has changed from looking for even perfect numbers to looking for Mersenne primes. Basically the same thing, because once you get one, it's very easy to get the other. And Mersenne primes, like I said, they're primes that are powers of 2 minus 1. So they're all of the form m sub p equals 2 to the p power minus 1. And it turns out that the exponent p has to be prime itself. That's not the Mersenne prime, that's its exponent. But it's pretty easy to prove that every power of 2 minus 1, in order for that number to be prime, then the exponent has to be prime. But the converse is not true. For instance, if you look at this list here, you'll notice that 11 is missing. I mean, the first four primes are 2, 3, 5, and 7. Those all yield percent primes. 2 squared minus 1 is 3. 2 cubed minus 1 is 7. 2 fifth minus 1 is 31. 2 to the 7th minus 1 is 127. What about 2 to the 11th minus 1? Well, it turns out that that's composite. That's 2,047, but that's equal to 23 times 89. So that is not a Mersenne prime. That's composite. And it turns out that most exponents do not yield Mersenne primes, but some of them do. And these are the ones that are known. There's only 51 known Mersenne primes today, and most of these have been found during the computer age. I'll get to that later. There were only 12 known, I think, before computers, the largest of which was 127. 2 to the 127th power minus 1. That's M127, if you like. That is known to be prime, and it was actually discovered by a French mathematician in the 19th century, Edouard Lucas, in 1876. And that's the largest, that's a prime with 39 digits. And that was the largest known prime for until the computer age, from 1876, I think, until 1951, 75 years. That was the largest prime known. And it was found by hand by Lucas. And Lucas actually came up with a test, a very famous test. It was modified by a 20th century mathematician named Derek Lamer. Now it's called the Lucas-Lamer test. But it's a test that is pretty easy to implement to determine whether or not a given Mersenne number with a given prime exponent is prime. And that's the test that's used when we look for these really big primes. Um, and there's a thing called GIMPs, Great Internet Mersenne Prime Search. Um, and this has been going on, I think, since the 90s, pretty much since the internet got started. And it's a big distributed program, and you can get your name on it if you want. If you want to discover a Mersenne prime, anybody can do this. All you have to do is reserve some range of prime exponents p, and look for a prime in some interval. But they're very, very hard to find. I mean, the last one was found, I think, in 2018. It's the largest known Mersenne prime to this date. The one I mentioned earlier, 2 to the 82,589,933 minus 1. That is known to be prime. I even have that written out here. This is the largest prime known today, and it has almost 25 million digits. I mean, I think it would fill a whole big book if you tried to write out all the digits. So it's a very, very large prime number. Um, anyway, and this is a graph of the size of the, this is actually the base 2 logarithm of the base 2 logarithm of the nth Mersenne prime and going up to 51. I think the largest Mersenne prime known is the 51st. And this is kind of interesting because this graph is very close to being linear. It looks like it's flattening out a little bit now, but for the most part, it's a pretty linear graph. And there's a lot of good reasons. A lot of mathematicians suspect that if we keep finding more and more Mersenne primes, that they should all fall on this line. I think it's just kind of a coincidence that we found a lot of exponents that are pretty close in recent years. Um, but anyway, yeah, and it's suspected. I mean, this is just a conjecture, but it's very strongly suspected that there's infinitely many Mersenne primes, although that hasn't been proven. We only know 51 of them now, but it's suspected there's infinitely many, and that they'll all fall on this line. And I should point out, log of log is a very, very slowly growing function. The actual Mersenne primes grow extremely fast. Like I said, largest one known, he has 25 million digits. So these are huge primes. And here's a list. This is a list of, I think, the top 20 known primes. And this list, I think, is a few years old. I don't even know if it lists. I think the highest one they have in here is the 848th prime. So this one's a few years old. But notice that the 10 largest known primes are all Mersenne primes. I think now it's the largest six. And, because the Lucas-Lehmer test, it's easy to determine whether a Mersenne number is prime. That's why I think ever since 1876, ever since Lucas he came up with a test and discovered, his percent prone to the 127th power minus one. It's been pretty easy to look for Mersenne primes, and that's why most of the largest known primes during the computer age have been Mersenne primes. There have been a few exceptions. I think the last one was from 1989 and 1992. At that time, I think there was a big gap between consecutive Mersenne primes, so nobody found any um, larger than the largest one that was known in 1980, 89. And then some computer scientists or mathematicians found some bigger primes that weren't Mersenne primes. But that's kind of rare. That doesn't happen very often. I think it happened again, I think in the early 50s, I think from 1951 to 1952, the largest known prime wasn't a Mersenne prime either. But those are the last two times that's happened in the last 100 years. And it's pretty rare, like I said. And I'm just going to finish by showing you a graph of the size of the largest known prime, which are usually Mersenne primes. And like I mentioned, Lucas in 1876 discovered his 39-digit prime, which is still the largest prime to ever be discovered by hand without the aid of machinery. Then, after the computer age, the size of the largest known prime started skyrocketing. These are all the records that have been made since the 1950s on the largest size of the largest known prime, which has mostly been Mersenne primes, and now it's 25 million digits. So we've gone from 39 digits to 25 million digits during the computer age. It's probably going to grow a lot more, especially once we get quantum computers. I have a feeling once we have quantum computers, we won't even be able to list all the Mersenne primes eventually because there'll just be so many. But anyway, that's my talk on perfect numbers and Mersenne primes. I hope you enjoyed it, and I'll see you next time.